for years that we would have an engineering and focus seminar series, and that idea became reality because Tamara's here. Otherwise, it was just in a dream. So she helped us kind of execute and put it together and brought the speakers in. So thanks, Tamara, for making it all happen. With that, Larry, it's all you. You can take it away. And thanks again for coming. I really appreciate it.
Thanks, Neil. That was a good introduction. This is working. Great. I'd like to welcome everyone here. My name is Larry Suppan, like Neil said, and I'm going to start from the beginning so we have a central point. It's just one slide here. This is when I was like 16, 17 years old, and I worked at McDonald's as a maintenance man, but I showed up. And the grill man wasn't there one day, so I ended up going on the grill. And because I stayed there, I ended up being swing manager there when I was 17 years old, 18 years old. So just showing up really, really helped. And I wanted to be a scientist. I'd taken all the math, science, calculus, everything like you guys. And I hadn't applied to any colleges, so my guidance counselor didn't really do her job or his job, and I just didn't know what I wanted to do. So I ended up talking to a naval recruiter. He took me in the back room, and I was a Trekkie, and they had James T. Kirk show me the submarine, the nuclear navy, and I was like, William Shatner. Oh my goodness, I was starstruck. I ended up joining the Navy and went to nuclear power school. First became an electronics technician, got to work with electronics. I thought that's pretty interesting. Went to nuclear power school, nuclear power prototype school. And I ended up going to a submarine. I did 4 patrols in the submarine. And you could see me on my last day on the submarine there, turning in my thermoluminescent dosimeter. That measures how much radiation I received. And I'm turning it in for the final time. So my last patrol, I had to think, what was I going to do now? You guys are already in college. I was like, am I going to go to college? Where am I going to go to college? I'd applied to 3 places. Simpson College, it's a Christian college, and was in San Francisco. I applied to Laterno. It was a engineering school that was Christian. And I applied to Cal Poly in San Luis Obispo. Yes. So I prayed about it. I really wanted to see what was going to happen. I actually visited all 3 schools. I ended up going to Cal Poly in San Luis Obispo. Before that, I got married. And we ended up going to Cal Poly. And I had to go through the interview process. I'd taken RF engineering, microwave engineering, as some of you will do that. It's a great, great major. I ended up interviewing to become an RF engineer at Wiltron, and it was in Morgan Hill, California. It was I'd gone through all the interviews. I thought I was killing it. And I got up to the CEO, and I'm thinking, okay, this is it. And Wiltron was bought by another company on Ritsu in Japan, and they went on a hiring freeze. So I had to start all over. So this is the normal stuff that happens, in life. So I just want to share some of that. So you got to always have a backup plan. You have to be prepared. So those great career fairs, I went to the last one, and I got a chance to talk to someone, and they were talking about superconducting electronics. This was 1990, it was the latest and greatest thing. It was happening in Silicon Valley, and I got to interview there. And I had 1 child at the time, 1 on the way, so they ended up hiring me. And it was really interesting because I couldn't go up to the Silicon Valley at the time. And I ended up having to go up a day a week and come back until my second child was born. And I got to be with the head of SQUID Electronics, and SQUID stands for Superconducting Quantum Interference Device. Measures very small magnetic fields. And he got with me 1 day a week, and he was teaching me physics and electronics, and he was an applied physicist. and it was so interesting. Everybody, there were two types of people at Conductus. It was a startup company, and there were only 16 people. I was the 16th person. So it was a startup, a lot going on. You had many hats. So I had to start the lab. I was the only person with the BS. The other person had a master's. I was the electrical engineer. He was the mechanical engineer. Everyone else was applied physicists and material scientists. So we were doing a lot of stuff. I was building the equipment so that they could do their lab tests. So it was a lot of fun. I got a chance to build Mr. Squid Electronics. That's right here. And there's the squid right there. And that squid, we initially had a dewar, which is essentially a thermos, and had bubbles coming out of it. And people thought it looked like a can of beer, so we changed it to a magnet. So it's much more conducive to undergraduate physics, and that's what it was used for. Mr. Squid, this is the chip, and this is Mr. Squid. Squid on a stick. It goes into a dewar and plugs into RS-232, goes into the back of this, and you connect it to an oscilloscope, and you can see all kinds of cool physics experiments. So I worked there for 3 years, maybe 3.5 years. You had to be pretty flexible. And I ended up joining the IEEE, well, I'd been in the IEEE from college, but I was in the Instrumentation and Measurement Society. And I was on the executive committee, and one of the things I had to do was get people to come up and give talks like this, but technical talks for the society. And I knew a lot of people with PhDs, because everyone in the company had one. So they took their rounds, and we came in and we talked about different things in superconductivity and RF microwave. They wanted to learn about A to D converters. So I went to this company called Maxim, and I talked to the director of applications. And I said, hey, we need to get someone to talk about A to D converters. Do you think you can come and talk for the Instrumentation and Measurement Society? And he said, sit down. And he pulled out an engineering pad, a green engineering pad, and he started asking me all these questions. So he had turned it around and made it an interview. So I was in Birkenstock. This is the Bay Area. So I was in I was a T-shirt and Birkenstocks at the time. This was a little underdressed for an interview. But from that, I ended up going to Maxim. But before that, I got to sort of play at engineering. I got to be a part of a paper. This is an instantaneous frequency measurement device, digital. It's called a DIFM, and it measures, identifies frequencies. When it's interrogated with a signal, it can break down all the frequencies, so you can know if the person's a friend or a foe because of the frequencies that they're using. And this went up in the Cassini probe, which burnt up in the atmosphere. So sometimes that happens. So Mr. Squid did make a splash in The Economist. It was the first high-temperature superconducting electronics system. And it won R&D 100. It made a big splash. And this is the team right here. This is when it had doubled. And it was a great team. It was a lot of fun. And of course, where am I? I'm right here. So you see this Conductus, right? Superconducting electronics. We had a softball team. We were in a D-League softball team in the Bay Area. And on the back, we had the squid. People were trying to figure out, what kind of mascot is this? And it said, too good to resist. That was our motto. So, and no one understood it. We had to explain it to everyone, so. But Mr. Squid. We did 23 years later, it's still around. That's the amazing thing. They're still selling it. My company, they're gone. They were acquired by another company. And the Mr. Squid, it's still around. So like I said, I got this interview at Maxim, and I ended up going in as a member of the technical staff. I worked in applications. There's many places you can work in a semiconductor company. You could be a test engineer as an electrical engineer. You can be an applications engineer, a design engineer, failure analysis engineer. There's so many different things. You can be an engineering manager. You need to be able to relate and talk with other people. Working with people is so important as an engineer, and collaborating. So I went from a member of the technical staff to an SMTS senior member, and I worked with a lot of the different analog components, A to D converters, D to A converters, power electronics, step up, step down converters. It was the first lithium-ion battery charger. I worked on interface projects, RS-232, RS-45. This is back in 1993. We started USB. It took a long time for that to happen. But those RS-232s were on every computer, and that was the bread and butter of Maxim. 1997, Maxim acquired Tektronix's facility in Beaverton, Oregon, that did semiconductors, and we moved up, or I moved up to start the fiber applications group, hired 12 engineers, and I had 3 technicians working. Did digital communications, laser drivers, transimpedance amplifiers, CDRs, clock data recovery, SerDes, serials, deserializers. So it was digital communications, 10 gigabits per second. If you have any questions, you can just interrupt me, but hopefully I didn't set the time. Okay. This is an eye diagram. And what an eye diagram is you take a pseudo-random bit stream, a bunch of ones all together, or 10, 10, 10, 10, and you superimpose them. So here's a 10, and here's a 1, 1, 1, 1, 1, 1, 1, 1, 0. So they're all superimposed, so you can see what kind of integrity, signal integrity you have by the jitter you have here, and by how open the eye is. So that's for digital communications. So some of the things that I did at Maxim is I wrote data sheets, I wrote articles in trade magazines. You see, I did a long line RS-45 transmission line. I got to do some experiments with an arbitrary waveform generator and created wave shapes that I would send down long lines, RS-45 twisted pair, and I would try to get it to have a good eye diagram at the end so you could see the data. You'd want to see the ones and zeros at the end of the eye. So once we got a really good signal, we put that into a chip, and that created, that's called preemphasis. You're putting something at the beginning, and you know that at the end of that line, you're gonna lose a lot of the high frequencies, the edges, and you're putting a lot of high frequencies in the front that you're gonna lose, and it ends up making it up at the end. And that was that. And then also did some data sheets. This is Maxim. This is a step-up DC to DC converter. Wrote the data sheet, road tested the part. I didn't design the part, but I road tested it, and I showed it to customers and helped to design those into boards. So that's what applications engineers do. Here's another one. And this one, I don't know, Maxim Integrated Products. It was called Maxim Integrated Products when it was founded. It changed to just Maxim, but it got confused with the magazine a lot. So they wanted to change that, so they changed it to Maxim Integrated. And actually, I downloaded this off the web, and Maxim no longer exists. Neither does Maxim Integrated. It was absorbed into analog devices. So there's a lot of, so just about every place I worked as an engineer. So there's a lot of change, so you got to keep changing, you got to keep learning, and you got to keep growing. So I worked here for 17 years. It was a great place to work. I loved being an application engineer. But in 2010, other things happened. You know, there's starting to be some layoffs. Dot-com bubble burst. People started, that was the first layoff. That was in 2000, 2001. First layoff of Maxim. Second one was 2008. Well, in 2010, they laid off 20% of the group of the high-frequency fiber and the RF group. And so I ended up needing to look for a job. I thought about looking for a job before, but I had golden handcuffs on. You guys know what golden handcuffs are? It's when you have all these stock options and you just can't leave because it's really, they make it hard. They put them out in the future and they start vesting and you're like, oh, I can't leave now. So I had a sabbatical, a great 9-month sabbatical. So I had to figure out what I wanted to do. You guys may be thinking about this. You guys are sophomores, freshmen, and there's probably some other ones, but I had to say, well, what do I want to do when I grow up? You know, so what do I want to have in a job? What don't I want to have? So I was thinking about it. I said, oh, I work with people. I work with people at McDonald's. I work with people in the Navy. I was the leading first-class petty officer. I ended up being a director, so I do like working with people. I like technology. I like engineering. I like teaching and training. I like to be able to think out loud and all of these things. I wanted to earn enough to pay the mortgage and to have a good work-life balance, all of that. And I wanted to have an organization with integrity. And this is what I wouldn't like. I'm not going to go over that, but these are things that I think most people really wouldn't like in a job. So these are the things I didn't want to have. And then I had to say, what kind of job title would I want? So I'm sort of thinking about that, and this is what I came up with, a team lead. So I'm a team lead now, so I've arrived. No. So second, I would be, okay, maybe I go back into engineering manager. Okay, I've done that. Or just be an electrical engineer, which is okay. That's fine. I thought about associate pastor. I was going to go into Christian ministry, and I feel like you can be a Christian minister as an engineer too. So whatever you do, do all to the glory of God. So I also thought about, and I may do this when I'm all retired, to be a math science teacher, because teaching is fun. So during that time that I had my sabbatical, I said, I need to prepare. I'd like to go back in the power industry, because I was in nuclear power, and that was one of the reasons I wanted. So I said, let me get back into the power industry. So I went and got a PE, professional engineering license. And you need a professional engineering license, apparently, to be a consultant or to be called an engineer in Oregon, which is sort of interesting. And I started a small consulting firm. It wasn't very long. It was sort of to keep me updated, sharp. I ended up doing a couple jobs, more pro bono. So I realized you got to not only do the engineering and design, but you also got to be marketing and promotion and all of that. So it was a lot more work than I thought it was going to be. But I ended up getting into power. I ended up getting a job at a fuel cell company called Clear Edge Power. And that was really interesting. It was another startup company, which I was a field electrical engineer in this one. And what I did was, when I was in the Navy, I was a reactor operator, so I had to look at all of these parameters and make sure the reactor was operating correctly. So I would look at them, analyze them, pull the rods out in whatever needed to happen to keep and maintain all of the equipment on for the reactor and the submarine. So this one, I would monitor 100 different fuel cells all over the country that were sold. These were 5 kilowatt units, about the size of a big refrigerator. And they would take natural gas and strip out the hydrogen, and it was a hydrogen fuel cell. And everything was contained in there. You had lube oil systems, mechanical systems, electrical systems. It was very interesting. But it was a startup company. Not many of those make it. And this one did not make it very far. It lost its subsidy from the state of California. And a lot of the green energy, I don't know if this is really considered green because you're using natural gas, but it was considered alternative energy. So it didn't make it. So this company, so I started looking for another job. And what I ended up doing is I had this job interview for Transom Technology. And Transom did online design systems. And for my job interview, they told me to act like it was from Transom and go to Maxim and do a presentation. And I had to do this in front of the whole company. So this is actually the first slide, and I'll show you a couple slides. But so I had to put this thing together and stand in front of the whole group, and I was hiring for a technical sales interview, or technical sales engineer. And so this was what I showed. I said, okay, I looked at I knew their data sheets, and I looked at an RF part, and I said, okay, you can have a doubly a simulation, you take the part, a 2630, you put the design requirements, what your input requirements are, and I was going to move this way, like that. So I put my design requirements in, my parameters. It comes out with a schematic. Now this is sort of proof of concept. It's a simple schematic that shows a few capacitors, the chip, and then I could actually simulate it by pressing a button on there, and I would be able to show some analysis. I'd say, what do I want to see? Let's say I want to see reflection coefficient, input and output reflection coefficients, 800 to 1100 megahertz. I could run that, and it can show me some Smith charts, which these are the Smith charts, and they're pretty much eye charts, except for this one, you can actually see something, but that's the noise figure. So I ended up getting this job. It was a very interesting job. Let me just finish this. You complete your design, you get the actual bill of materials here, and then you can buy the chip. You could buy an EV kit and do some other things with it. But like I was saying, Maxim is no longer Maxim. So every place I worked for as an electrical engineer, you got to be flexible. It's no longer around in name. So the next place I was going to work at, I wanted to make sure it was going to be around. Well, it started in 1776. So it's definitely going to be around. I think it's going to outlast me, this one. So George Washington actually commissioned the Army Corps of Engineers. And what they do a lot of different things. They build a lot of things. But the area that I want to focus on is hydropower. But they do navigation. They have all kinds of engineers, biologists. They got forest rangers. They got, there's just so many things that they do. But like I said, I want to focus on hydropower, specifically the Hydroelectric Design Center. And that's what this is, HDC. See, I'm getting power out of water. That's what that symbol means. So what we do is we're going to refurbish the fleet that's been built. A lot of it's been done many, many years ago, in the 30s, 40s, 50s, and 60s, some of it in the 80s. A lot of that stuff, the equipment's older and it needs to be refurbished. So we're supposed to be experts in the field, and I'm going to talk about these, but these are some of the, we've got, switch yards with breakers, We've got the control room where the hydropower, everything's under control. These are pen stocks at, this looks like it's Chief Joseph. This is a rotor pulled out of the hole where the generator goes. This is a crane. You'll see a little bit more about this as we go. And this is me sitting in my cube here. Again, I work down on First and Oak, and I'm a team lead, so it's a lot of fun. I'm working with a lot of new engineers just out of school. What I had to do when I came to the Corps, because I was more in electronics, I was going to be a power engineer. So when you go to the Corps of Engineers, they actually put you in a program for 2 years. A lot of times, you know, you're getting your license to learn your degree, but when you go to a company, they're going to train you for what you're going to do. And you've already shown that you could do something, you can learn something, so they're hoping that you're going to be able to build on what you've learned, and you've got the foundation. So I went and I became an EIT, and I used to joke I was the oldest living EIT with a PE. And it was true, I think. So this is sort of what engineering design competency, FTE. When you're an engineer, you need to know engineering economics, because you need to be able to make money for the company. You guys, I'm sure you guys learn about economics, you learn about all of that kind of stuff. FTE, what that stands for is full-time engineer. So we have to figure out how many engineers do we need next year? How much work do we have? It all has to be balanced out. So full-time engineers, you could see this is where we built, and now we're just on this kind of growth plan. We've got 40 to 45 million in our design program, and these are all of the plants. The size of the circle is how much power it produces, but they're all over. There's 75 plants all over. We produce the power. There's Corps of Engineers, there are operators. You can actually work at one of the power plants as an electrical engineer. You work in the what do they call it? The technical center at the project. We produce the power. The power authority will sell the power. That's like BPA, Bonneville Power Authority. We produce it, they sell it, they market it. This right here, electrical, these are all the branches here in the Hydroelectric Design Center. I'm in the power systems. There's protection systems, control systems, generation equipment. We have 40 cyber engineers and scientists, 60 electrical engineers, 60 mechanical engineers, and that is the largest concentration here in the entire Corps of Engineers. It's right here. So these are the products that we put out. I've done half of these. I've done studies, plans and specs, source selection, selecting contractors, engineering during construction. This is some of the cool equipment. This right here is a runner, state-of-the-art runner. That's on the bottom of the hydroelectric generator. Water turns. This is a fixed type of runner. All of these bags, that's for testing the crane. It's testing the weight. It's a lot of weight. They could be. This could be. I'm not sure if it's stainless steel or Inconel or something like that. It's a. I think it could be stainless steel, but I'm not sure. I know we fix the current runners. We fill it in with stainless steel, because you get cavitation on these things, pitting. This right here is the stator of the hydro generator. Hydropower, a lot of advantages. Okay. This right here is where the water flows. You got a lot of potential energy, because this is higher than here. You're converting that potential energy to kinetic energy. The turbine turns the generator, generates electricity, goes out over the lines. Same thing. They're pulling a rotor with that crane, lifting it out. These are the pole pieces. It's like an electromagnet, excuse me, and that's north, south, north, south, north, south, all the way around, like that. This is a pole. This is one of those poles right there. Yes. Yes, and then this right here, this is the stator. These are laminations, and the stator doesn't have the coils in it. Right here, the coils are put into it. So that's where, so a moving magnetic, Faraday's law, moving magnetic field induces into conductors, electricity, induces a current. So you get three-phase current. Okay, there's other things that happen. You get relays. Do you guys have questions? Should I stop right here? What do you think? Keep going? Okay, good. So there are relays. When you have a power system, you want the breaker to open that's closest to the fault. So you have to set those relays. You have to do some analysis. You have to go and check what all the short circuit current is in the entire power system and make sure that the interrupt rating for every one of those breakers can handle it so it doesn't blow up and arc across. So that's part of power system design. You've got, this is for arc flash. This is what can happen when you get a short, and it's not good. And what you have here is a time current curve, and to the left of it means you're not going to have a breaker open. To the right it does. And you see how each one of these is like, this is called coordination. This is closest to the fault, or this is like downstream, and this is upstream. So, and the same way, this is upstream up here, and this is downstream. Like this breaker, this breaker, this breaker. That would be like that. The governor controls the turbine, controls the wicket gates and the power that's generated. The exciter controls the generator. It feeds, it takes a little bit that's produced by the power, turns it back into DC, sends it into the rotor that generates the electromagnetic, the north-south poles. So, and then you have control systems. This is all electrical engineering, control systems. It can be mechanical too. And all of this has to be recorded. You need lots of data. So you take that data and you try to match it to a predicted thing and then what you actually get to make sure your models work so you can predict what happens. And then you can, when you're uprating something, you got to make sure if you're putting more turns on the generator, you're going to get more power out. You got to make sure your entire system can handle it, and that's called a powertrain analysis. These are transformers. Transformers take voltage or power. They take voltage and they'll take it from low to high or high to low. And when you transmit over power lines, you don't want to transmit with a lot of current because I squared R losses. So what you can do is you can increase the voltage really high so it takes a lot less current. Voltage times current is power. So you have the same amount of power and you have a lot less losses. That's why we use these transformers. And that's what our system was set up by Tesla. So these are common projects that we do. And I've done the ones that are in red since I've been there. And I've been there for 8 years now. So it's been a lot of fun. Now, you got to take all that data. How do you get it? It's SCADA. You've got a lot of information. You do complete models like this, and these are electrical engineers doing this. You get all this SCADA programming. You get ladder logic. You use PLCs. All of that stuff is used. Those are all electrical engineering type projects. These are transformers. This is when you do a factory acceptance test. You go to the factory, and then you go and you install it. It's called commissioning. And these are other types of systems that are outside, switch yards, breakers. Let's see, this is DC systems. These are motor control centers. This is for station service that supplies the dam all of the power to run all of the systems so the hydro generator works in the powerhouse. And this is the DC system. These are batteries right here. And here we're doing a load test on a crane. I've been working on a lot of cranes late. I'm going to be going to Montreal to go to a factory acceptance test in October, first week of October. And I am finishing here. This is my submarine. It's on the grassy knoll now. And this is me at Columbia Park, just at our picnic for the Corps. And sort of nostalgic, I'm actually wearing my submarine hat that I just got mailed to me. So, but anyway.
Where is the submarine now?
This is in Kings Bay, Georgia, on the grass. Yeah. I haven't been there yet, but I mean, that's where I used to be. I would go out. That was the port. So does anyone have any questions? I tried to go as fast. Yes. Is it just half the submarine or the whole submarine? It's just the top fairing. This is the fairing up on the top, and this is there's two hulls. There's a pressure hull, and then there's a superstructure. It's just the top superstructure. And it doesn't go down into the ground. It's just for looks.
So the reason we're using a mic is for people that have to watch it on the video.
I should have repeated that question. He was asking about the submarine. Yeah, I can do that. Yes. Supervisory acquisition system, data acquisition system, something like that. I can't even think of what I've said it so often, but it's you're just taking all of that information from all of the sensors in your system, and you're just aggregating it so that you can use it. It's doing data analysis and everything. Yeah, but and it's actually, SCADA has different components that people have, and then you can program it at a higher level language. Yes. What was the transition from going to superconductors, semiconductors to power generation like? That was a great transition. It was, when you're an electrical engineer, you've got to keep learning. You do, and a lot of the principles are the same. Believe it or not, reflections in RF happen on transmission lines. They're long transmission lines. They get reflections too. I studied for the PE, and I just looked through it, and I had a lot of friends that I could talk to them about it. I neglected to say this, but networking is so important. Professor Natsky, I actually went to the lab, and we were doing some measurements after that 2010 time when I was in between jobs, and I got in there and started making some RF measurements, and that was a great help to sort of get back into it. So that was when I was thinking about going into RF. But then when I got into power, I was willing to learn, being teachable. They'll ask you questions. I did come from the Navy, so I had been in nuclear power. So that sort of probably got me into that fuel cell company a little easier, especially since I should let you know, it was between two people at the end. And as one last thing for the interview, they gave us an Excel spreadsheet with 10,000 lines of data. And they said, extract as much information as you can get out of it. And it was from that they decided who was going to get the job. Yeah. Yeah. Learn your Excel, definitely. You can do anything with Excel, actually, believe it or not. And yes?
Yeah, I got a design question for you.
Yes.
How come you don't use a spherical design? Because wouldn't there be more surface area to charge it better?
Okay, so you said in a hydro generator, you've got a turbine that turns the shaft up to the generator?
Yeah, which turns like the cylinder in that magnetic chamber.
Right.
How come you don't use a spherical design? With a spherical design, wouldn't there be more like surface area to charge more magnets?
You're talking about spherical, like
Yeah, like a
spherical.
spherical.
Well, I mean, I think it's how you would manufacture it. There could be, I mean, partial, you know, you have got to move these, the stator, you got to change you got to update it. And that's one of the hardest things. Let me just give you an example of something. We have one slant axis hydro generator. It's slant axis. And you won't believe, we have to try to pull that thing out now. And it is extremely difficult. The idea was you could have the water running through it and then pump it up, pump storage, pump it back up to the higher level. And there was some fish issues when they did that, so they decided not to do that. And but it needed 2 cranes, and it had to be exactly balanced to pull this thing out. So if you did something spherical, I think mechanically just getting that, there may be a way, but I can't foresee it right now. It's a lot easier to pull something out when it's straight up and down. So, I mean, and these things weigh 800 tons. I mean, and that's why we are doing a lot of cranes right now, because we have to make sure the cranes are able to do it after 50, 60 years to lift these things out. And it's sort of, you get the cranes done, and then you pull the rotors and refurbish them.
Couple more questions.
Yes, right here.
How would you compare the power capabilities of nuclear and hydro?
Oh, that's a good question. Comparing the power capabilities of nuclear and hydro. I like both of them, having been in both of them. Nuclear is pretty condensed, and I believe it's pretty good on the environment if you control the fuel. The power density is pretty high. It's different in Canada than it is here. We enrich our uranium, whereas Canada just sort of takes it bulk, and they do things a lot differently. They'll change the control rods when the reactor's operating. So it's a completely different, they use a lot more land. We actually shut down and change the control rods and all of that, and the fuel out of it. Hydro, I mean, you talk about renewable, that is the most renewable energy, I think, and you can use it 24/7. And without the hydro balancing the grid, you're not going to get solar or wind, because because solar and wind, you know, you got sun, you got a lot of power. Well, you got to balance that grid real time. You can't over voltage, so you need to drop hydro generators off. You can do that. You can do dynamic loading. You can't do dynamic loading on a nuclear power plant. It's not good. You get xenon transients and various things. So you want to operate the nuclear power plant at 100% all the time. So, did you have a...
I'm going to cut you off. You can ask. I'm glad you guys have more questions. Larry. Oh, thank you. I'm going to cut you guys off. Some of you had 3 o'clock classes and other things, and I know that. I'm glad for the questions. Couple quick comments in closing. Number one, the vision, part of the vision for these seminar series is that these folks would come in and literally get the fire hose out and just spray you with it. And I feel like that happened. Like, that's a fire hose of information right there in 45 minutes. It's unbelievable. And you'd be a little bit overwhelmed by that. That's great. Second question is double E's, junior or senior double E's? Raise your hands so I know. Okay, did you guys get most of that? I'm hearing some semis, yeah. Freshmen, did you guys get most of that? No, that's what's supposed to happen in a couple years here. These seminars are targeted at the upperclassmen, exactly what we wanted from Larry, perfect. And we wanted you freshmen to be like, whoa, like there's a lot I don't know, but also there's a lot that I could know. There's a lot of super exciting, I I want to go back to school and become an electrical engineer. I'm not messing around. I don't think I could take Dr. Natsky's class, actually. I would pass it. But I think this is going to happen to me in every one of these, because I see these now and I think, man, I don't know any of this stuff, and it'd be really fun to learn it. So we hope that you get exposed to these things in a way that you're like maybe intrigued, and it'll help you decide your major a little bit for the freshmen. And for you seniors and juniors, just like you're closer to having this kind of journey yourself. Let's give a big thanks to Larry for coming out. Larry, if someone wanted to set their sights, I might want to work for the Army Corps someday. In closing, what steps would you tell them to take now if they think that's a cool job to work at the Army Corps?
You can be an intern while you're an undergraduate there and work there during the summer. They're pretty good at that. Just find out more about it. Find out more about it. They're online, Hydroelectric Design Center. That's what I would do.
It's amazing to think how many they're employing. Like, that's a huge, huge company there, really, that's taking care of things. And you were talking about one of the 9 boxes you put up there that you're working in. Yeah. Okay. Thanks, you guys. Larry will be around for questions. See you.